Yep, thank you. Hello, everyone. I'm Aiden Grossman. I'm currently an undergraduate student at UC Davis, and today I'm going to be presenting on LLVM IR-Dataset-Utils, which is scalable tooling to build and analyze large IR datasets. So a little bit of an outline of what we're going to be talking about today. Just quick note, lots of different people have helped collaborate on this, contributed ideas, code, infrastructure to help make this all work. Downstream applications. So yeah, lots of people have helped work on this. They're on the paper that we have up on arXiv too. So first off, we need to sort of define what problem we're actually going to try and solve before we go out and solve it. So one of the key things that we were looking at when we were originally looking at making this was ML models are becoming bigger, transformers are becoming a big thing, and they need a massive amount of data to train. We want to make them work on LLVM-IR. There's no real way to collect a massive amount of IR that existed. We also saw that a lot of compiler analyses looking at the performance of heuristics or magic constants within heuristics were kind of bespoke, and we wanted to create infrastructure to help make those make it easier to test on a larger section of code and also across languages. And then there are other efforts like translation validation and cost modeling that can benefit from having additional data. And we believe that having scalable tooling for creating and analyzing large data sets of LLVM-IR can help solve these problems. So just to compile, so this is the data set that we created using this tooling. It's available on Hugging Face using the link that you see there. So it's a ready-made data set. You can just go and download it. It's permissively licensed, like Apache 2, MIT, BSD3 clause, and BSD2 clause. And it's about 600 gigabytes of bitcode, which is, reasonable amount. Data set distribution. So when we actually run the tooling and build it, so this is what gets distributed. We get more before we filter based on licensing. But yeah, we get up, lots of Rust, C and C++ somewhat get filtered out due to licensing issues. Quite a bit of Julia, and Swift doesn't really build that well in Linux, so we don't end up with a whole lot of it. So moving on to IR extraction so that we can actually build the data set. So the general philosophy is we want to run the normal build process for the packages that we're trying to include in the data set. We want to interface with the normal build system and just take advantage of the infrastructure that's set up there and try and build it using as close to what people would actually use in production as possible, minus a couple compiler flags that we need to set that shouldn't actually end up impacting anything. So we pass flags to extract bitcode as early on in the pipeline as possible. So ideally, directly after the front end does code gen into IR without any passes running on it, with the idea being if we want to get something later on in the pipeline, we can always just run opt with whatever passes we're interested in on it. If we want assembly, we can just do that, run LLC. Getting bitcode, it's easy to manipulate, and it keeps and right after the front end keeps everything flexible. We extract the bitcode into a corpus, which we'll get into a little bit later, and then we collect a bunch of different projects and combine them all into a large data set. So for the tooling that we use for this is MLGo utilities, so machine learning guided optimization utilities. It came out of creating corpuses for individual projects. So this actually recently got upstreamed into the LLVM mono repo under the directory that you see there. And it can extract IR from projects in a variety of different cases. If you're using CMake and you can get out a structured compilation database, that's ideal because you're getting the information from the build system on the exact files that you care about in most cases. We can also do loose bitcode files, and we can also handle cases that we don't end up needing for building the data set, like thin LTO. So for extracting C and C++ IR, we build with Clang because that's the standard C, C++ LLVM front end. So we pass xclang fembed bitcode equals all. So out in the object file, you'll get a point LLVM-BC and a point LLVM-CMD section. So the LLVM-BC section contains the bitcode representation of that object file directly after the front end. And then we extract the IR from the object files in the build directory. Like if we're doing that with a CMake invocation, we end up going in and we try and pull the structured compilation database, and otherwise we just loop through and try and find all the object files, which is a little bit more dangerous because you can run into some weird object files from things like CMake tests and whatnot. And then we also extract compilation command lines and include them in the corpus, depending upon what stage you're at. Right now we're not actually propagating them all the way through, and there can be issues with the compilation command lines because it includes a lot of paths that are specific to the build directory, so it's not a very portable representation. For extracting Julia's IR, it ends up being quite a bit more complicated because Julia's compilation model is very different from a traditional AOT compiler. So they somewhat call it an AOT JIT. I guess that's kind of oxymoronic. But essentially the code gets JITted as it's needed. So you get types and all of that at runtime. And then, the types aren't known until runtime. And then once you call a function, it gets JITted. But there's been a recent effort within Julia to push to get things pre-compiled to decrease startup time because compiling things at runtime is reasonably expensive. So we take advantage of that. We have a custom patch within Julia to extract bitcode at the relevant stage in the pipeline. And then we use the pre-compilation tools, so essentially whatever the packages have set up what they have set up for functions that pre-compile, we extract all those. And then we also run the unit tests that are available with the package since Julia has this consistent system to do that to force lowering of the functions in the tests, which is maybe not purely representative of what kind of bitcode you'd end up getting if you run the Julia in the real world, but we believe it's a reasonable approximation. So the IR from Julia has some caveats, so it hasn't been run through the Julia legalization process at this point. So like the opt pipeline will usually run fine, but if you try and lower it with LLC, it'll usually fail because you need to run another Julia pass on it. And the opt pipeline doesn't really make sense to run on Julia code due to how they represent their calling conventions. So IPO passes, they don't actually run any in their pipeline because they create correctness issues due to how they represent their calling conventions. Extracting Rust IR, we used cargo and then build all the individual targets in the projects that we can find, emitting LLVM bitcode and we explicitly tell it to not run any LLVM passes with the -C no pre-populate passes. And we build stuff in debug mode to prevent any optimization so we can get stuff early on since there's no support. Well, there's kind of support for bitcode embedding, but it doesn't end up working that well. And then for Swift, we have to do a couple different things since Apple's changed some stuff up since they were using bitcode embedding. So we're building release mode. We use a similar flag to Clang, which is also supported in Swift, where we just tell it to embed the bitcode. And then we specify some stuff with the modules because the default mode in Swift doesn't actually work as you would expect, doesn't work with bitcode embedding. And then, we turn on no optimizations to prevent anything from interfering with the IR that we're getting out. And then after that, we sort of introduced this concept of a builder, which is an abstraction over a package ecosystem. So it handles a couple different things. So it will handle dependencies needed to build a package when necessary. So if a package needs dependency X in order to build properly, the builder is responsible for handling that. It's responsible for actually invoking all the command line tools to build everything, extracting the resulting bitcode into a corpus using the MLGo utilities, and then logging build information like failures, since there ends up being a lot of them for further analysis later on. And builders are specific to a package ecosystem or a build system rather than a language, because something like C and C++, you have a bunch of different package ecosystems and a bunch of different build systems rather than a single one, where something like Rust, cargo is kind of synonymous with the language. So it's still specific to a package ecosystem. It's just that's the main package ecosystem used with the language. And then scaling this, we want to actually build a large IR data set containing a bunch of different packages rather than individual packages. So we have some general scaling principles here. We use the array package to distribute everything across multiple nodes when available. We design it to split across a bunch of different nodes. We built everything primarily on HPC systems, and you have to build a lot of code. So it ends up taking quite a few core hours, like building quite a few of them. It would maybe be about 24 hours of 32 to 64 nodes that were usually about 48 cores each. And then one of the other things, it's a scalable distributed system. So we want to handle failures gracefully, but also make sure we're logging all of them because we want to be able to analyze it later and see if there's too many failure cases in one spot. If it's an issue with the tooling or just a package that won't build because we bumped to the Clang version and suddenly something that was originally a warning turned into an error and stuff isn't building after that. So if we're building a bunch of C and C++ packages, we want to support more package ecosystems in the future. But right now we focus on using the HPC package manager SPAC. So essentially it's a from source package manager. So downloads source and then invokes the build system and everything. So that gives us about 5,000 C and C++ packages, mostly specific to Linux and HPC workloads. So a lot of packages fail to build, maybe 1,000, 2,000, mostly from what I've seen due to Clang GCC compatibility issues or things like GCC is hard-coded into the make file of a small project. So there's just a bunch of stuff like that that would be really expensive to go in and fix. And yeah, we're looking into other sources of vetted C and C++ in the future, primarily looking at Linux distributions to get another source of real-world code that people working in compilers will probably care about. For Rust, we have a builder for arbitrary cargo packages. So we just take the entirety of crates.io. We take all the packages and then we clone them all and try and build every single target and every single one. It works reasonably well. There's a lot of individual targets failing for various reasons. Sometimes there's different flags that you need to set or whether or not you enable features or whatnot. And we haven't done any fuzzing to figure out to increase the build rate, but stuff works reasonably well. We get a lot of IR out of Rust, and it scales pretty well too. And for Julia, we take all of the packages on Julia Hub, and there's about 8,000 to 9,000 or so on there. Building Julia packages is probably the most expensive part of the whole thing. Just because we're doing things like running unit tests, which are very expensive compared to just building everything. And then for Swift, we're using the Swift package index and the Swift package manager to handle dependency management. It works reasonably well. We don't get a lot of bitcode out of it, and there's a lot of failures, but that's mostly because we're doing this on Linux HPC systems, and Swift is mostly used on Mac. So there's a bunch of packages that'll depend on things like Swift UI, which you just can't get on Linux. And there's a bunch of other issues like that that we run into with building Swift packages. I haven't looked into all of the failures too closely since there's a couple thousand. But when I looked at them, that was the general gist of the issues. And then we have a couple bespoke builders for individual large projects that people are interested in. Like in the data set, we include recipes for things like Chrome and Firefox as they're big projects and people care about them. They run on a lot of devices. They take up a lot of storage. They take up a lot of CPU cycles distributed across all the devices. So we support CMake, auto tools, and shell commands to build things like Chromium and Firefox where it's their own build system. And we specify the individual projects in JSON using a format that's specific to the builder that you're interested in. So you just get a JSON file. You run the commands as you would for everything else, and it just ends up setting up the jobs and it'll build it. So after building the data set using that, you end up with the data set. The last time I ran all the tooling, we ended up with a data set of about 1 terabyte of LLVM IR 990 gigabytes. And then you want to do some analysis on it. So we built some analysis tooling for this. So it's designed to scale, again, multiple nodes. So it scales reasonably well. There's some issues depending upon the analysis that you're running and how you do your batching and whatnot. So it works on data sets built from source. The Hugging Face version, the format ends up being different, and the tooling currently doesn't support that, but it shouldn't be too difficult to get that working. So we can do a variety of different function and module level analyses. So some of the ones that we've worked on before. So we've done pass mutation frequency by language. So looking at, you can see some interesting patterns like what passes trigger where, like memcopy optimization triggers significantly more on Rust, which was reasonably known, but it's nice to be able to confirm that on a large corpus. We can look at things like opcode distribution. You see some kind of interesting things there. We can look at function property distribution, like the number of top-level loops, the number of floating point instructions. You'll see I have a slide of that next. We can also look at things like function duplication. So we can look at like function properties where you'll have you can look at the number of instructions, like basic blocks, like top-level loops. Like you can see like C and C++, like have significantly more top-level loops than other languages, at least in the tail. So there's a couple interesting patterns like that. The analysis itself might not be super interesting, but it sort of shows the idea of you can run these sorts of analyses on a massive amount of IR and collect it on like code as a whole rather than an individual project, which might be biased by specific coding patterns or like the language that's used. That did not render how I hoped it would. It's supposed to be squares, but we've also done like an analysis on function duplication, so within and between languages. So like you can see, like within languages, you get a pretty high rate of duplication, and this is post-module level deduplication. And you can see some interesting patterns where like Swift and C++ actually have a decent amount of overlap. And there was a case earlier where people were interested in looking at, we didn't end up performing the analysis, but where people were interested in doing, implementing a merge functions pass. And like something like this would be able to show you like within a module, like what kind of gains can you expect to get with that kind of optimization. It gets a little bit more complicated since most stuff in the real world was shipped with things like thin LTO, and we're not accounting for that. But it can give you sort of a rough idea on code as a whole. And then, after that, we have code. This is mostly on our end for license considerations when we want to release the data set. But if you're interested in building it yourself and you want to filter by license, or you want to increase the amount of licenses that you're looking at, if you don't want to just use the whole raw data set, we have license filtering. So if you're distributing it, you need to comply by licenses, make sure the license is actually there. If it's a license that requires attribution and the license to be copied over, you need to distribute that with the data set. Like things like avoiding AGPL. So we have tooling to filter by license and pull things out as necessary. So for determining licenses, each corpus manifest, so essentially each project manifest that we describe, we specify a license with that. So we pull that from a variety of sources depending upon what package ecosystem we're building. So like Rust crates, the metadata is stored within the package ecosystem, and some of them might not be. So like Julia, the information is not stored in the package ecosystem. So we essentially go to GitHub and query the API for all the Git repositories. And we also look at the license file. We need to make sure, because like the licenses, they require attribution. So we go in, we find the license file, and we're able to pull that out and make sure that it's actually there in the repository so that we can assume that like someone didn't just misclick when selecting the license on the package ecosystem. So we consider it license compliant if it's licensed under MIT Apache 2 BSD3 clause or BSD2 clause currently. And we have a top level file matching that license ID based on it's about a 90% match that we expect to have in order to assume that like that project is under that license. So actually running this, we have the code in a GitHub PR right now as like a contribution to the mono repo. We have a landing page with more information on the data set. And with some other links, we have some initial documentation. There's not too much written there, and I need to write some stuff up. We also have a RFC for an incubator project under the LLVM umbrella. We're trying to push to get this as another incubator project under the LLVM umbrella. So if you're interested in this or the data set itself, the RFC, a comment on the RFC expressing your interest would be appreciated. So a couple future directions that we're interested in looking at, the code quality for the data set or for the data set utilities is not particularly great currently. It was a summer project and there wasn't a lot of code review and there needs to be more testing and whatnot. And we also want to add source code mapping. So we have prototypes for that for C and C++. We're able to get like all of the preprocessed source connected to C and C++ files. So that works reasonably well. There still needs to be a couple issues. Rust and Julia and other languages are harder to do that because there's not necessarily a single source file to bitcode file mapping, which makes things significantly more complicated, but we're interested in maybe figuring that out. More C++ sources from Linux distros, capturing of link time dependencies, looking at Fortran. There's a couple other pieces of work that have been presented here. Using the data set, we think there's a lot of opportunity in using large data to do lots of different analyses. And lots of other people have helped work with this and performed at Lawrence Livermore National Lab. Questions?
I think
thanks for the talk. You've mentioned that you've had to build the Rust data set in debug mode. Did the debug info kind of interfere with the purpose due to the bitcode size increase? And are there any analysis opportunities provided by this? For example, the mapping back to the source in any way, or has it been more of a case, more of a trade-off case that, well, we need the Rust data set, we'll have to go with the debug info, and it doesn't really get in the way of the actual optimizations?
Yeah, so for what we've done currently, the debug info doesn't matter. It probably inflates the size by a decent amount. I haven't done an analysis on like what kind of sizing we get if we strip all the debug info, but I would expect it to go down by a reasonable amount. But for like the stuff that we're working on, like opt will essentially just, like all of the analyses that we've done so far and the other work, we'll essentially just ignore the debug info. Like all the downstream tasks that we've done, it'll end up just getting discarded. So yeah, and we can write like source mappings and other it's hard to do the source mapping when you don't have the source anymore. But yeah, there could be a couple analyses that like we could do with that. And with the tooling, like it's theoretically extensible. So if you want to like get like C and C++ sources with debug info and work on the mapping back to that, like you can just change a couple flags in how you build it, rebuild the corpus, and then you can do that sort of analysis.
So, great talk. I was kind of curious about the part where you had about function duplication.
Mm-hmm.
Have you looked at the final binary to see if the results actually holds there? Because in certain languages like C++, for example, you're going to see a lot of duplication due to templates. And then via the language rules, a bunch of those just go disappear. And depending on your linker as well, your linker can actually come in and deduplicate functions in other fun ways too. So have you looked into the correlation between intermediate formats and actual binary output at all, or is that something you have on the roadmap? Or
yeah, so we did an analysis at some point where we ran like opt 03 and then compared the function duplication before and afterwards. Doing it at the binary level would be interesting, but we haven't looked into that at all. I forget what the results are. Probably I forget where they are, and I'm forgetting the exact details of the result, like the comparison between 03 and like just doing it directly after, like with the bitcode that's stored in the repository. I think the function duplication went down a little bit, like as stuff got pruned. But yeah, it's an interesting analysis, and yeah, something that we have not really looked into that deeply yet.
Cool. One more question while I'm just standing here, if that's okay. Another thing is in your charts where you show the kind of distributions of what kinds of instructions appear. I think that's pretty cool. But you have a very large data corpus of different programs, right? So do you have a sense of see you have like a bunch of floating point instructions in some languages more so than other. You'd expect more in Julia, for example, naturally. But in other languages, do you have like a sense of what kinds of programs are being written in your corpus? Julia, so C and C++, like we're taking it from SPAC, so it's primarily HPC applications where you'd expect things like lots of blasts and lots of numerical computing and whatnot. But we haven't really looked too deeply into like, these are the sorts of applications that we have in here. And it might be interesting to cluster by application at some point, but we haven't really looked into that yet. Awesome. Cool. Well, thank you very much.
Yeah, thank you.
Other questions? I have one. Can this corpus be used to analyze for security properties?
Yeah, so I mean, like looking at like compiler security hardenings, you definitely could do that. Like with Christoph's like Bolt security analyzer, like you could take all the code, lower it to different targets, retarget. Yeah, you'd have to retarget it because it's built on x86. But reasonably you can do. You can reasonably just lower it and then run something like that to check that the security hardenings are enabled. So.
Okay, thank you very much.